So we're going to talk about solubility and Ksp. These are special kinds of equilibria. So we talked about equilibrium in general, we talked about acid-base equilibria. Now this is a new kind of equilibrium where we're trying to dissolve a solid salt, so a solid ion compound. So let's take this, for example, this solubility equilibrium. We're trying to dissolve calcium fluoride solid, that's on the left, and we're going to dissolve it and form its aqueous ions. We're going to dissolve it in water. So what you see here is a lattice where the ions are stuck together. So this would be a solid, what the solid would look like, right? An ionic lattice. If we put a crystal of calcium fluoride into a beaker and we fill it up with water, like we've done here, then what we know is that some of those ions separate, and they'll continue to separate. Dissolution equals the precipitation. So once those rates are equal, then we're at a point called equilibrium that we've already learned a lot about. At equilibrium, the rate of dissolution equals the rate of precipitation. The solution is said to be saturated. So a saturated solution at a given temperature is one where you cannot dissolve any more ions in the solution. It is as concentrated as it can be at that temperature. The concentration of that saturated solution is considered the solubility of that salt at that temperature. So there are a lot of, if you Google solubility, it'll say the solubility of calcium fluoride at 25 degrees is this many grams in a liter. Okay, so that would be the concentration of the saturated solution. So that's just some terms. If you know the molarity of each of those ions at equilibrium in the saturated solution, then you would plug those ion concentrations in as molarities into the equilibrium constant expression, which we call Ksp. Ksp is a constant, and in this case it is equal to the calcium ion concentration times the fluoride ion concentration squared. The Sp in Ksp, the S stands for solubility since it's a solubility equilibrium, and the P stands for product, because in a solubility equilibrium expression, the expression for Ksp no longer has a denominator because the single reactant, calcium fluoride, is a solid, and so pure solids and pure liquids do not appear in the equilibrium constant expression. Therefore, this is simply a product of the two ion concentrations raised to their respective stoichiometric coefficient powers. Now these are some various Ksp values for some ionic compounds at 25 degrees. Most Ksp tables are for 25 degrees. The Ksp value will change with temperature, but at a given temperature it is a constant. So you can see various numbers there. Aluminum hydroxide has a very low Ksp, 1.9 times 10 to the minus 33. That means that that solubility equilibrium lies far to the left, which means it is a very insoluble salt, not very much you're going to get in the aqueous phase. And then on this table, the highest solubility or the highest Ksp on this table is either lead chloride or silver sulfate, which both appear to be about 1.2 times 10 to the minus 5. So you can see there's a large variability in Ksps in terms of their magnitude. Now the higher the Ksp, the higher the concentration of ions in solution. And so this is Ksp here. And the concentration of these ions in solution, that's the aqueous side, right? That's the right-hand side. So the larger K is, the further to the right this equilibrium lies, and the more soluble the salt will be, right? So you have more ions in solution that lies further to the right, which is the aqueous side. That's a more soluble salt. These are the solubility product values that you're going to get. The table, this is the top of the table, this is the bottom of the table. So it'll be one piece of paper, one side, and these are the values that you will use for your quizzes and your homeworks and your exams. This is the end. Sorry, I guess it's about 2.5 slides long, but it's only one. Now, if you're doing a calculation, this little flow chart will help. If you're given the solubility of a compound in grams per liter or in moles per liter, then this will show you, that's on the left-hand side. You can convert that into the concentration of ions and then plug that into the Ksp expression to solve for Ksp. Or you might be given the Ksp value and you're expected to tell me and solve for the solubility of the compound in either moles per liter or grams per liter. So we have a few examples, calculations here that we are going to. So we're going to do some solubility and Ksp calculations. start with this first one. We're given a concentration of a saturated solution. Saturated implies that the solid is in equilibrium with the aqueous phase. So that's where Ksp would be relevant. So we're going to write the solubility equilibrium, lanthanum plus 3 and 3 fluoride ions on the right-hand side in the aqueous phase. The solid salt is on the left. If we write the corresponding Ksp expression, remember only the aqueous ions appear, the solid does not appear. And of course the 3 stoichiometric coefficient becomes a cubed in the problem. So the lanthanum fluoride concentration 9.6 times 10 to the minus 3. It looks like I should have written 9.3 times 10 to the minus 6. I apologize for that. That's going to be equal to, however, the lanthanum concentration. You don't do anything to that, so it would also be 9.3 times 10 to the minus 6. The fluoride ion concentration you would multiply by 3, and that would give you 2.79. That's if you do 9.3 times 10 to the minus 6. I accidentally wrote a 6 there. It should be, but the 2.79 times 10 to the minus 5 is the right number. And that gives you 2.0, no, it should be 2.0 times 10 to the minus 19. The original number, 2.0 times 10 to the minus 19, is the answer to this problem if you use the 9.3. I kind of had a little brain conniption and wrote 9.6 in this problem, and then I guess I readjusted my numbers for the 9.6, not realizing that I had written it down wrong. So the answer, if you plug in the original number, 9.3 times 10 to the minus 6, the answer should be 2.0 times 10 to the minus 19. Now, if you're using 9.6 times 10 to the minus 6, like I accidentally did here, when you multiply that by 3, you do get 2.88 times 10 to the minus 5, like it shows here. And then if we cube that, and we multiply it by 9.6 times 10 to the minus 6, that does give you 2.29 times 10 to the minus 19, which would round to 2.3 times 10 to the minus 19. It should have 2 sig figs because the number you're given has 2. So again, 2.3 times 10 to the minus 19 if you accidentally use this 9.6 times 10 to the minus 6 number like I had, or the original number I had, the 2.0, that was the right answer if you plugged in this correct number. Sorry for that mistake. I'll try not to let it happen again. Calculate solubility in grams per liter of barium carbonate in water at 25 degrees. Now here we're going in the opposite direction. We're going to have to look up the Ksp for barium carbonate, and we're going to write the solubility equilibrium and the Ksp expression. It's really important that you guys can do this. We'll set up an ice table. This left-hand column doesn't matter because the solid doesn't appear in the Ksp expression. And we're going to write 0 and 0 for the initial concentration of barium and carbonate because we're trying to dissolve it in water. We're going to do a plus x and a plus x for both sides because it's a 1-to-1 stoichiometry, which means that the Ksp is equal to x squared. So these are relatively simple algebraic expressions that you're going to solve for. You can look up Ksp on the table. We're going to look up barium carbonate, which appears to be near here, right up here at the top, near the top, 2.6 times 10 to the minus 9. So we're going to take the square root of 2.6 times 10 to the minus 9, and that's going to give us the molar solubility of barium carbonate. And then we're going to have to, so we'll take the square root of that, and that gives us 5.099 times 10 to the minus 5 moles per liter. We're going to convert that into grams per liter because that's what the problem is asking us for. So we need to multiply this by the molecular weight, which is 197.31 grams per mole. Moles cancel and you get grams per liter. 1.0 times 10 to the minus 2 grams per liter. 2 sig figs because the Ksp value we're given has 2 sig figs. A little bit more solubility practice here. So we're going to do a problem in the lab. You mix together some barium nitrate and some sodium fluoride, and the question is, will a barium fluoride precipitate or not, or form or not? And so remember, solubility equilibria, these are just an application of general equilibria related problems. So this question is asking you, when you mix these two together, is the system at equilibrium? If it's not at equilibrium, will it proceed to the right or to the left as it achieves equilibrium? So this is really a question about reaction quotient. It's a question about Q, okay? So you're given equilibrium concentrations, you're given concentrations that are mixed together, and you're asked, are we at equilibrium or not? Which is basically what it's saying. Is it going to precipitate or is it not going to precipitate? So that's what we're going to look at here. This is about Q. So we have our barium and our fluoride mixed in, and we need to calculate the barium concentration. We need to calculate the fluoride concentration. The reaction quotient, Q, would be the product of barium times fluoride squared. So we're going to calculate the concentration of barium when we mix them together, which means we need M1V1 equals M2V2 to calculate the total barium concentration, 0.02 molar times 25 mils divided by 50, which is our total the total volume. When we mix two 25 milliliter volumes together, we get 50. The fluoride concentration, we're going to do the same thing. M2 equals M1 times V1 divided by V2, which gives us 0.01 molar. And the barium concentration is also 0.01 molar. So we're going to plug those values in. Q is 0.01 times 0.01 squared, which gives us 1 times 10 to the minus 6. Now you need to compare it to K, right? So this is Q, we compare to K, remember just like back in chapter 13. So we're going to look up barium fluoride, that's here, 1.8 times 10 to the minus 7. So our Q value is larger than this. It is 1 times 10 to the minus 6. K is 1.8 times 10 to the minus 7, which is definitely smaller than Q. So that means that Q is greater than K, which means we have too many ions in solution, which means the reaction will proceed to the left. It will precipitate. So these will coalesce and form a precipitate. Because Q is greater than K, the reaction proceeds to the left, which is the solid side. Precipitation of barium sulfide, barium fluoride. So that's what this is showing you here. We have a barium fluoride precipitate that forms here. That's a solid.